Today I'm going to talk about a random sample and why we use them in statistics. Now, why use a sample? Selecting a sample is less time consuming than selecting every item in the population. Just think about it. We only ask everyone in the United States about different questions in their life once every 10 years. The reason is that it's a very costly task to go around, knock on everyone's household, count all the members of the household, ask them several questions, find out their age, how much they earn, who are they married to, who are they related to. This can be a very timely, costly effort. So instead, what we do is we ask a smaller group of people when we want to find out questions about members of the United States or other countries by taking a random sample. So it's less costly than selecting every item in the population. Considering the era of big data, a simple computer may not be able to handle an entire population. So instead, we take a smaller subset of that much larger population to try to get some idea of what the population looks like. An analysis of a sample is less cumbersome and more practical than analysis of the entire population. What is the sampling frame? Sampling frame is a listing of items that make up the population, compiled from data sources such as population lists, directories, or maps. For example, if we wanted to know some facts about students at the University of Louisville, one thing we could use is the list of students that are in the University of Louisville. Or let's say we want to restrict it to only the members of the College of Business. Then we can look at all of those students who are registered for classes in the College of Business. That would be our sampling frame. Inaccurate or biased results can result if a frame excludes certain portions of the population, or you use a different frame to generate different data. Let's talk about the different types of samples. There are non-probability samples, which are often made just due to pure judgment or convenience. And then there are the ones that we use for scientific purposes, which are probability samples. And these can come in four different variants: a simple random sample, a systematic sample, a stratified sample, and a cluster. In a non-probability sample, items included are chosen without regard to their probability of occurrence. For convenience sampling, we may just find a group of people that are very close by at that time instead of truly randomizing and picking people at random. So for example, maybe I do want to know some things about students in the College of Business. Instead of sampling students from across all different courses, out of convenience, I may just ask the individuals that are in this class. It's cheap, it's easy, it's inexpensive, don't have to make a lot of judgments, and I can still get results. Judgment sampling is much worse. In judgment sampling, you decide who stays in your group and who leaves your group. This could very much bias your results. In other words, you get to voice an opinion of who is an actual expert in your group in those subject matters. These are not very good to use. Probability sampling, which is what we're going to be mainly using in this class, includes a simple random sample, systematic, stratified, and clusters. The difference here is that individuals are chosen with a finite or fixed probability. So that way everyone may have some chance of being selected. This is more representative of what a population would actually look like when we grab our sample. Simple random sample. Every individual or item from the frame has an equal chance of being selected. Selection may be with replacement, so you select individuals, is returned to the frame for possible reselection, or without replacement. That means once a person is selected, they cannot be chosen again. If you happen to have a very small population, sometimes with replacement is necessary in order to get a large enough sample size. If you have a very large population, thus you're going to grab a fairly large sample, without replacement is the better option. Samples are generated selected based on a table of random numbers, or a computer random number generator. So for example, we can go into Excel and we can create random numbers using the random number generator, or we can use a special sheet called a random number sheet. Here's an example of one. You're going to notice that on the left-hand side, we have a sampling frame, a list of individuals from 1 to 850. So these are the members of the population. Now what we want to do is grab a subsample of these folks. In order to do that, we're going to use a random number table. In order to do that, we have to first determine what is the highest value we'll be willing to accept. Well, if we only have 850 individuals in our total population, we have to ignore any values that are greater than 850 and move on to the next one. And then we go over to a random number table. What we do is we start selecting each set of numbers by the first three. So the first item that we're going to grab is person 492. The next one we're going to grab is person 889. The next person we're going to grab is person 357. The next person we're going to grab is 002, so person number 2. The next person we will grab is 811, and so on and so forth. You could also grab numbers going in between spaces. So for example, we could have said 492 and then 808, since 808 is part of our group. However, we would have to ignore number 892 since that's beyond our 850 and skip over to the next value, which would be 435. That's also an acceptable way of grabbing a random sample. Systematic sample. You decide on the sample size, which is going to be little n, and we'll always use little n for the sample size. Divide the frame of size n into these smaller subgroups, in other words, k subgroups. And then from there, we would always pick a person given their order in the group. So in this example, we can say that we're going to collect information from members of the College of Business. And what we're going to do is we're going to choose every 7th student within each class. So every 7th student within each class will be part of our group. Now this may not be truly representative of what the population looks like, but it's pretty easy and at least somewhat random since we are replacing a probability on each individual in order to construct the sample. Stratified sampling is a little bit better. In this case, you divide the population into 2 or more subgroups according to some common characteristics. And then within that subgroup, you select a random sample. So just like we did for the simple random sample, except now you're doing it within each subgroup. The reason this could be useful is that you may have underrepresented groups that would typically be missed if we use just a simple random sample. But if you use a stratified sample, you're guaranteed to have some representatives from that subgroup within your sample. So it will be more representative of the population. Clustered sampling is actually a more similar to systematic sampling. You divide the population into several clusters. Let's call them cities for right now. Each a miniature version of the actual population. And then you select from those cities. So that means everyone in those cities would be included within your sample. Rather than randomly selecting individuals, you're actually randomly selecting clusters. Here's the comparison between the 3 primary ways that we collect samples. For simple random sample and systematic sampling, it's pretty easy to do. You just use your random number generator and you select that person. It still may not be a good representation of population due to their underlying characteristics. So for example, if we are looking at people in Scandinavia and they have very, very few Africans or very, very few Latinos in their population, we may miss them entirely. However, if we use a stratified sample, we can say that we're going to grab a proportion of folks from those underrepresented groups. This ensures a representation of individuals across the entire population are found within the sample. Clustered sample is more cost-effective, but it's less efficient than stratified sampling. Here, what we're doing is we're still selecting large groups of people, however, we're treating each group as being randomly selected. Surveys. Evaluating worthiness of surveys. What is the purpose of the survey? is one question you may have to ask yourself. Is it actually going to provide useful information? Is the survey based on a probability sample? In other words, are they actually randomly choosing individuals, or are they only choosing individuals that may lead to a certain result for their survey? How can we avoid or reduce errors? Well, one, we have to determine the appropriate frame. So who are the people you want to answer the survey? You follow up on non-responders. Non-responders may be not responding at random, but sometimes they're not responding because they have some underlying reasons. So, for example, let's say we want to know the use of illicit drugs in a community. How many people do you think, when you survey them, would truthfully tell you their drug use? It could be that non responders are heavy drug users. We can do the same thing with drinking or sexual behavior. In each one of these sensitive areas, people tend to lie or tend to not respond to avoid lying, which would then lead to systematic differences in your sample versus what's actually happening in the population. Third, you need to construct good questions that elicit good responses. For example, you can't bias your question right from the get-go. You can't say things like, people who believe in capital punishment are absolute idiots. Do you believe in capital punishment? Yes or no? Right? You're already anchoring people to answer that question in a biased manner. And then lastly, sampling error always exists. And that is the one part that we get to live with, but we have ways of reducing that. For example, if we increase the sample size, we're going to get closer and closer to the population. Eventually, if we were able to ask everyone in the population, there would be no sampling error. Survey and error types. The first version of the error type is the coverage error type. This is called selection bias. Some groups or individuals are excluded from the frame and have no chance of being selected. One example of this would be a survey of wages. Right? If we decided to ask people what their wages were, and we looked at characteristics about these folks to try to figure out what are the components of a wage, a group of people we may end up excluding are the unemployed. Now, the unemployed simply haven't found a wage yet that they're willing to work at, or that someone's willing to extend to them. This group here does want to work, right? Thus they're unemployed. They do want to work, they just don't have a job yet. This would be a problem in our coverage. There's a selection bias. Another example would be if we want to find out how well does high school GPA predict college GPA, but we only ask individuals who are at college. We'd be ignoring the subset of individuals who had some type of high school GPA because they were still high school graduates but didn't go to college. We wouldn't be answering the question correctly. The second version is the non-response error. People who do not respond may be different from those who do respond. Where I have seen this quite a lot is in clinical trials. When you think about a clinical trial, you often have two groups, the experimental group and the placebo group. Now, people voluntarily participate in these clinical trials, which means they can exit these clinical trials whenever they like. However, that creates a problem, because the only folks who would actually stay in the clinical trial are ones who believe that they're getting some benefit from participation. And that's going to include individuals who are in the placebo group. So what would happen is that you would start off with a group that initially, due to random sampling, looked more or less alike. But as time goes on, all the sick individuals, the folks who are not getting better, tend to leave both groups, which means that the average health in both groups tends to rise, even if the drug itself has no benefit whatsoever. So even if we were to have two randomized groups, both of them receiving placebo, but we tell them that there is an experimental group, we'll still see health improvements on average only because the individuals who are very sick will leave those groups, leaving the healthy individuals left and the average rising because of it. Other versions of error are sampling error. Now this is just normal error. This happens all the time. Normal variations from sample to sample always exist. So for example, if we were to go ahead and ask 10 individuals in this class what their height was and record what their height is, and then we go ahead and find the mean height. And then we ask another 10 individuals what their height are also in this class. Do you believe we'd find the same exact height? No, there would probably be some small difference between these two means. That's the sampling error. However, if we were to ask everybody in the classroom what their height was, and then we took an average, and asked those same folks even seconds later again what their height is, we would get the same exact height. In other words, in the population, there is no sampling error. We get the true mean. But when we take subsets of that population, different subsets that is, we're going to get different means for height or for the thing that we're looking for. That is the sampling error, those differences within those individual sample means. Lastly, there's measurement error. Measurement error can come about from three different reasons. One is weakness in the question design. You may have had one intention for a particular question, but people understood it the wrong way. Second is respondent error. Sometimes people get really tired of doing surveys and they start putting in abagadabba. Another version of measurement error is simply recall problems. So for example, if I were to ask you how much income did you make last week, or how much income did you make over the past year, could you tell me what your income was down to the very cent? No, you'd probably round. But rounding still produces measurement error. You're not giving me the true adjusted income that you'd report, say, to the IRS. That's the true measure. You're going to give me a rounded number. That rounded number will produce measurement error. We see the same thing happen with weight. People don't really know what their weight is, but they know more or less what they weigh. Same thing with height. They know more or less what their height is, but not their exact height. That produces some noise, some error. The last thing is the Hawthorne effect. So the interview effects on the respondent. They can kind of lead the respondent to go towards a certain response. Or the respondent tries to appease the interviewer by responding in a particular way. Examples of sampling errors. The surveyor randomly selects people who are shorter than him, thereby excluding everyone who is taller than him. You randomly survey university students about their high school GPA to find out how high school GPA affects college admission. However, you are ignoring all the other individuals who have a high school GPA but are not in college. You conduct telephone interviews about people's drug use and crime life, assuming that they would actually be truthful about those things. Sampling distributions. A sampling distribution is a distribution of the individual's probabilities of all of the possible values of a sample statistic for a given size sample selected from a population. Example, if you're looking for the average age of students in this class, a sample mean could be the highest possible mean, not very likely, the lowest possible mean, also not very likely, and something in between. This goes back to the example I was giving with the heights. Although we can ask 10 different people each time in the classroom what their height is and take its mean, there are going to be some extreme groups in there, but more often than not, we're going to find values that are relatively close to one another, which should be close to the actual population mean. So here's an example. Assume a population with just size of n. That means there's only 4 people in this world. And let's label these 4 people A, B, C, and D. So let's let x be a random variable representing the age of the individuals. The values of x are going to be 18 years old, 20 years old, 22 years old, 24 years. What is the distribution of all possible means of a sample of size 2? That means if we randomly select 2 individuals from this world of 4, what are the potential different means that we get from that small sample? So let's do the math. We know that the population mean is going to be 18 plus 20 plus 22 plus 24 divided by 4 because we had 4 individuals. So the population mean will be 21 years old. And we can also find the population standard deviation by taking 21 and subtracting it from 18 and squaring it, 20, subtracting it from 21, squaring it. 22, subtracting it from 21, squaring it. 24, subtracting from 21, squaring it. Adding all those up together and dividing by 4, then taking its square root would give us 2.24. Now, each person in this population has an equal probability of being selected. That is, every person has a 25% chance of being selected for the sample. So now let's consider all possible samples of size 2. The person who is 18 years old can get matched again with another 18-year-old. The person that's 18-year-old can get matched with the 20-year-old, can get matched with the 22-year-old, and the 24-year-old. And we can do this for each row. Now let's calculate the means for each one of these groups. Notice that we're doing this example with replacement. So we would have 18 for individual 1 and 18 for individual 2, which should give us a mean of 18. We would have 18 for individual 1 and 20 for individual 2, which will give us a mean of 19, and so on and so forth. So that's how we're getting all of these means here. Okay. Notice that we do have some extreme values. All right. We have a 24 in this corner and an 18 in this corner. This is the low and this is the high. But we have a lot of values that are right around the population mean of 21. So how are those sample means distributed? Well, let's look at the likelihood of each one of these means, and let's go ahead and make a histogram associated with those means. All right, so we only have one observation out of a total of 16. That is 18. So this is 1 over 16, correct? Same thing with 24. We have 1 over 24. Now we have 2 19s, so that's 1/8, and 2 23s, which is also 1/8. We have 3 20s and 3 22s. Meanwhile, sitting in the center, roughly about 0.25% of the data are at 21, which happens to be the population mean. So that means that our sample means do approach the population mean. They also seem to appear to be normally distributed. That's going to be very important for us as we move forward. So now we have to discuss a new statistic. Before we knew what a standard deviation is, now we're going to talk about a standard deviation that's specific. It's a standard deviation for x bar, the standard deviation of the sample mean. Now the standard error, that's what we call this standard deviation of the sample mean. It has that special name. The standard error is a measure of the variability in the mean from sample to sample. Notice that it decreases as the sample size increases, and this should make sense because as little n approaches big N, meaning it goes all the way to the population size, we should have a standard error that goes to 0. Why? Well, let's think back to our example of looking at heights of individuals in our classroom. If we ask everyone their height in the classroom and 10 seconds later we ask everyone their height again, we should get the same mean because we're finding the population mean. So as n gets very, very large, what we're doing is we're increasing our sample until we're covering everyone that's in the population, which means that eventually each one of those samples should produce the population mean. So if a population is normally distributed with mean mu and standard deviation sigma, the sampling distribution will also be normally distributed. This is a key insight that we're going to use over and over again, and it has a name. It's called the central limit theorem. I'll discuss this further in the upcoming slides. But first, let's talk about the math when it comes to the standard error. So again, the standard error is the standard deviation of the sample mean. Let's let the variance of x equals sigma squared. All right, so this is the variance of the population. Let's let alpha be a constant, like a number, 1, 2, 4, 5, one that doesn't move. It's not a random variable. then the variance of alpha times x, remember x is the random variable, is going to be alpha squared times the variance of x, which is sigma squared. Let each x be independently distributed. That means each x is independently chosen. If that's the case, then the variance of x1 plus x2 will just be the sum of their parts. Since they're independent, they have no covariance. So then we would add up their two variances, which would be 2 times sigma squared. So if we believe all that, let's ask the question, what is the variance of x bar? Meaning, what is the variance of the sample mean? The variance of the sample mean can be broken down to the actual formula of what the mean is, which is 1 over n, the sum of all the x's. Now we can treat 1 over n as this alpha, this constant. So we can bring it out and square it, which is 1 over n squared. Next, we have to remember that this x here is really x1 plus x2 plus x3 plus x4. Now each one of those x's, those x1s, x2s, they each have the same variance. So they're all sigma squared, but we have n of them, right? Because we're counting n different x's, which will leave us to n times sigma squared divided by n squared. If we cancel out that n and this n squared, we'll end up with sigma squared over n, and then if we take the square root of that, which gives us the standard deviation, we get sigma over the square root of n, which is exactly the formula for our standard error. This leads us to our sampling distribution of x bar. And we're going to bring back an old friend, our z-statistic. Now it's going to work the same way. We're going to use our observed value, which in this case is now a sample mean, x bar. We're going to have our claim, or our population mean, over on the right-hand side. That tells us the deviation. And we're going to divide through by the standard deviation. The only difference is that we're talking about the standard deviation of x bar, which is the standard error. So the theory behind it hasn't changed. You have your observed sample value, you have your population value, and then you have the standard deviation of that observed sample value. In this case, it just happens to be x bar minus mu divided by the standard error, which is sigma over the square root of n. So here are some properties of the sampling distribution. For normal population distributions, if the x is normal, x bar must be normal as well. It also has a smaller standard deviation, which means it's closer to the center. As the sample size grows, this becomes tighter and tighter, meaning we get closer and closer around mu. And as the sample size becomes smaller, the standard deviation grows, or the standard error in this case, so the distribution becomes wider and wider. So given mu is equal to 368 and sigma is equal to 15 and n is equal to 25, between what values does 95% of the sample mean lie? Well, if you recall, for 95%, we want 2.5% in the lower tail and 2.5% in the upper tail. If we do that, that means that we have to have a z value of 1.96. So we're going to use this 1.96 along with our z formula. And we place it right here, 1.96. We need to calculate the standard error, and we need to plug in mu. Given that, we can find these x bar values. So when we do that, we get the lower bound for x bar, which is going to be mu plus z, which in our case is 1.96, times the standard error, or 368 plus a negative 1.96 times 15 divided by the square root of 25, which is an x bar lower bound of 362.12. And we could do the same thing for the upper bound, only this time we are adding instead of subtracting, which will be 373.88. Therefore, 95% of all sample means of sample size 25 are between 362.12 and 373.88. The sampling distribution for non-normal populations can still look like a regular normal distribution. So even if the population is not normal, thanks to the central limit theorem that states that the means of samples from that population will be approximately normal as long as the sample size is large enough. Okay, so then what's large enough? Well, if the population shape is normal, then we can still use the old rule. If the population is normal, the sample distribution for the sample mean also must be normal. If the population shape is at least symmetric around mu, then we only need a sample size of about 15 or greater in order to get the sample mean to have a normal distribution. And if the population is not normal or not known, then we need a sample size of at least 30 or greater in order for the sampling distribution to be approximated by normal. So suppose a random sample of size n is equal to 36 is selected from a population with mean mu at 8 and a standard deviation of 3. Given that n is greater than 36, we know the central limit theorem is going to hold. What is the probability that the sample mean is between 7.8 and 8.2? Well, we can find this. We can find this by calculating our z's, meaning that we can take 7.8, subtract off 8, and then calculate the standard error. Divide through, and that gives us our lower bound for z, and do the same thing for the upper bound. So this is how we go about doing it. Not knowing the shape of the population, the central limit theorem can be used. Since the sample size is greater than 30, the sampling distribution of x bar is going to be approximately normal. We're going to say that mu of x bar is equal to mu is equal to 8, and that the standard deviation, meaning the standard error here, would be equal to 3 divided by the square root of n. Square root of n is going to be 36, which the square root of that is going to be 6, and 3 divided by 6 gives us 0.5. So we're going to take 7.8 minus 8 divided by 0.5, which gives us a z value of 0.14. We do the same thing for the upper bound, which gives a positive value of 0.4. And then we want to find the probability that our z falls between negative 0.4 and positive 0.4, which is the same thing as saying the probability that z is less than 0.4, which we get from our table, minus the probability that z is less than negative 0.4, which we also get from our table. We find those probabilities in the table, subtract them from each other, and get the value in between, which in this case would be 31.1%. Sampling distributions of non-normal populations. Solution, we don't know what the population looks like. We grab a random sample, but we do know that the sample means follow a normal distribution. From there we can back out what is the likelihood of the population mean falling between those 2 points. Now we can do the same thing for population proportions. A population proportion is the part of the population sharing a characteristic. So, for example, what is the percent of females in the population? What is the percent of Latinos in the population? What is the percent of dog owners in the population? The sample proportion would then be the proportion of individuals within our sample who, for example, have pets or are female. This provides us an estimate for pi, approximately a normal distribution when n is large. Now, what does n being large mean in this case? Well, here we have two bounds we must satisfy. N times pi must be greater than 5, and n times 1 minus pi must be greater than 5. This means that extreme values of pi won't follow the normal distribution. So for example, let's say that pi is very close to 0, very, very close to 0. In that case, n would have to be very large in order to satisfy this constraint. So think of a number such as 0.00001. n would have to be very large to satisfy this 5 constraint. Likewise, if n is very large, so 0.999, then this lower bound may not be satisfied. In other words, we can only use this approximation for values of pi that are relatively in the center. We find the same rules as we did before. We can still calculate our z statistic using proportions, only now our standard deviation is going to be pi times 1 minus pi divided by n, and our mu is going to be equal to pi. So here's our example. If the true proportion of voters who support Proposition A is equal to 40%, what is the probability that a sample of size 200 yields a sample proportion between 40% and 45%? So here we're saying that if pi is equal to 0.4 and n is equal to 200, what is the probability that the sample proportion will fall between 40% and 45%? So first we need to calculate the standard error. We use our pi, our claim, our population pi, which was 0.4. So that's going to be 0.4 times 0.6, or 0.24 divided by 200, and the square root of that. In this case, we get 0.03464. We then use that standard error, and we compare our two pi's. So our first pi, or p here, was 0.4 minus the actual pi, which is 0.4, and that gives us 0 on this lower bound. And in the upper bound, we want p to be equal to 0.45 minus still pi, which is 0.4. We divide through. This allows us to use the z-table. Now we want to find the probability that z is in between 0 and 1.44, which is the same thing as saying, what is the probability that z is less than 1.44, and what is the probability that z is less than 0? Now, since z is a standard normal, we already know what the lower bound is. Right? The probability that z is less than 0, where 0 is exactly in the center, is 0.5. So we only really need to find the probability that z is less than 1.4. In our case, that's going to work out to be 0.4251. Again, we only care about this region right here. All right? We already know that this is 50%. All the values of z less than 0 have to have a cumulative probability of 0.5. So what we want to know is what's the likelihood that z is going to be less than that, between 0 and 1.4. Alright, well maybe you still don't believe that what I've done here is real, that this is just a theory. So, I went ahead and I generated a population, if you will, or a random sample, using a uniform distribution. And these are values that are uniformly distributed between 0 and 1. Okay? And I grabbed 150 observations. So I created 150 observations for this particular set. So think of a population that has 150 individuals in it, and they each have values that range somewhere between 0 and 1. Right, notice that there is still lots of variation in here, and this thing does not look like a normal distribution. So now I'm going to do the following. We're going to now randomly select 10 samples, each containing 27 observations. That means out of the 150 individuals, I'm going to collect 27 people with replacement. So I'm going to go through, select 27, calculate a mean, dump those 27 back into the population, and grab another sample of 27, calculate a new mean. I'm going to do this 10 times. This is the picture I get when I do that. So this is the histogram of those 10 samples, each sample again having 27 observations in it. This doesn't look very normal yet. Okay? And remember, our sample size should be greater than 10, right? Our sample size has to be closer to 30 before we start getting something. So let's increase that number of the samples to 50, keeping the same number of observations within each sample. So we're still going to stick each sample at 27, but now we're going to grab 50 of these guys and make X bars. Now look what's going on. Still not quite normal, not the pretty normal you'd get, but you start to see that picture popping up. Now you start to see that bell curve moving itself in. So let's push it. Now instead of 50, let's go all the way to 100. So we're still just grabbing 27 observations, calculating the mean, dumping those 27 back, and doing it again. We do this 100 times. Now look at the picture. This looks a whole lot like a normal distribution with its extreme values, and this center is sitting pretty close to 0.5. So here, when we started off with a population that clearly was not normal, we can still show that the sample means approach a normal bell curve. And so this is the example of the central limit theorem working. We started with a uniform distribution. Next, we sample from this distribution and calculate means. Then, as we increase the number of samples, the histogram of the means looked more like the normal distribution. So here's our chapter summary. We discussed probability and non-probability samples. We described 4 common probability samples, which include systematic, simple, clustered, and stratified. We examined survey worthiness and type of survey errors. We introduced sampling distribution. We described the sampling distribution of the mean. We talked about both the sampling distribution of normal populations as well as non-normal populations where we applied the central limit theorem. We described the sampling distribution of a proportion, and we calculated probabilities using the sampling distribution, meaning that of X bar. In the next chapter, we will talk about interval estimation within chapter 8.